Okay, hello everybody. Good morning. Thank you very much for inviting me for this talk here. I'd like to talk about the idea we've been following for quite a few years. It's like, how can we manage the ever-increasing numbers of images in a different way than we do it normally? So first, I want to introduce my team. Basically, it's me and a colleague, a professor, and we get two PhD students. Actually, Konstantin is here and Nico is in Berlin. And our main research areas are information retrieval, machine learning, and we're doing visualization and image sorting and image navigation. This is our field. Actually, this is the point where we are living in Berlin. You might not know this, but I'm just showing this area view because usually as humans, we are quite familiar of looking at landscapes or maps, and I'll come back to this later in the talk. So the main challenges of image search basically are today that we have an ever-increasing number of images. You can see that it's pretty big. This is the number of images that have been taken in 2022. But you might say, well, this might be, but what do I have to do with this? But even on your personal devices, usually you have up to over 2,000 images on your phone. But if you come to stock agencies, that's even worse because there sometimes you want to find your images. And you can see they got millions of images over there. Shutterstock is leading with almost 400 million images, and so you don't have any idea how they look like. Do you have an idea how many images these are? Any guesses? So actually, these are 350,000 images. This was an installation in a place in Berlin by a Dutch artist. And this was the amount of images that are uploaded on Flickr daily at that time. So these images actually do exist, but it's quite different than times when we printed them. And so if you have an agency with millions of images, this has several consequences. This means nobody has ever seen all the images. It's just impossible. You cannot get an overview. And if you want to explore these collections, the only thing you can do is just scroll through this list, and they're all not organized. For example, these are fish images I've looked up on Shutterstock some months ago. They are not organized. It's a big mess of everything, and there might be very good images, but it's very hard to find them. And the humans are very good at looking at one or two images, so usually we have to navigate in the world, so we are used to that, but we are not able at all to look at many images at the same time. So this is a collection of CD covers. These are 800 covers. And if you're looking for a particular cover, so usually it's a little bit difficult finding something here. And this is the reason why usually, if you're looking at humans, you have to come below 20 images to be able to recognize anything. So, and this is the reason on normal web pages and also on e-commerce, typically you don't have more than 10 images at a time. And this is a kind of bad situation because this is an e-commerce web page where they have over 10,000 jeans images and products, and they're showing 3 of them. And they ask you to scroll, but if you scroll, perhaps you see 20 or something. This means you're only seeing a very, very tiny fraction of the entire set. And so it's a bad situation. What can we do there? So the main problems of image search is that most images, if they are taken, they are untagged. This means we need some automatic understanding of these images. And if we have a nice description, we can do automatic searches. And the other problem is we have still far too many images. We need some kind of organizing them in a nice way that we can navigate them. So the basic principle of image search is shown here. So we have these images. From these images, we have a feature extraction scheme. They're stored, and then if I have query image, I'm also computing the features, and then I'm making a similarity search. This means finding similar features, and then these images are displayed to the user. But we have several challenges here. The problem is, how do we compute good feature vectors? Another problem is, how do we make the search fast? And how do we show the results to the user? And how can we possibly do a nice interaction with that? So this brings me to these 3 blocks as shown on the right I'm going to talk about. The first thing is a search for the good feature vector. What does it mean? A good feature vector is something which is a correct description of an image, which shows the content and the appearance of the image. And it should be very close to our perception because we are searching something. It should be suitable for all kinds of images that we have. And if we want to compare different schemes, this needs to be accessible. We need to have an evaluation to see how good the feature vector is. In the very beginning, people used very low-level feature vectors like tile descriptions from MPEG 7 that you're seeing here. like the layout or the histogram or the most dominant colors of an image. There have been local systems like GIST and other things. The problem was that with these primitive systems, we found very poor search results. So this looks quite similar. You can see the arrangements are the same and the colors are the same, and they have some relationships, but that's that's not what you're looking for. And this is basically due to the semantic gap. And a lot of people always thought that this semantic gap could never be closed, but this has changed at the advent of neural networks. In 2014, this was the first paper where people proposed to use neural network. And the idea was pretty simple. They just said, okay, if we have a normal convolutional network here, we could just take one of these last layers or even the last one and take this as a future vector. And then we use this for searching images. And there have been a few other papers from then on. The kind of bad problem of this was that in the very beginning, people started using landmarks for evaluating image retrieval systems, which is somewhat biased. Because if you go to a normal stock photo agency, you find everything like faces and natural objects and a lot of other things. We have far many images than just landmarks. And this means we need something else to be able to evaluate this system for all kinds of images. Here's a little comparison of some test sets that are out there. Some landmark images, some varying things like cars and very specialized things that only birds and that only specialized people could recognize, and faces. And they're all very special for particular purposes, but they're all kind of mixed. So they don't have anything which is good for everything. And this brought us to the idea we should have a new test set which is good for all kinds of images. So we want to have a very large diversity of images and classes. And it should be kind of simple, because if we cannot tell the difference between two birds, it's perhaps only for very special people. But we want to have classes that should be accessible by non-experts. Actually, we did this last year and proposed a system made up from these 6 sets shown here. And I want to show you what can be done with this new test set. So you're seeing some example images from the set. So it's a wide variety of like sketches and natural photos and also landscapes and icons and logos and objects and faces. So what we did is we just took this set and then we took 2 networks that you might know. Derk is very famous from Google. They put all their efforts into that to make a very good landmark detection and description scheme. It was very sophisticated, and even they did 5 times images of different scales. And then we took a normal ResNet 152 image, which was trained with ImageNet 20K, but nothing else. And then we actually evaluated that. And then we saw that the first thing that comes to mind here is that DAG was pretty slow compared to the normal system because of all this special treatment. It was very good for landmarks, but it was pretty bad for all the other categories that made up this set. And even the normal ResNet system here was better than this DAG system compared for this average set of typical images. So this means that landmark systems are good for finding landmark images, but it doesn't really help in the normal world. So what can we then do? If you accept that we should focus on all kinds of images and not only landmark, what can we do to improve these general purpose feature vectors? The first thing we could do is just use better networks. Over the time, there have been better networks. And you can see on the right that the MAP, the mean average position, improved with that. The next thing you could do is just take a larger set of training data. And if you do that, it will get better again. So this is quite nice. Let's just keep on doing that, and then it will get perfect. We got a little problem there because the creation of single label data set is very difficult and takes a lot of money on time and students doing that. Nobody wants to do that. And the other problem is if you have an image like that, the woman was a dog on a street in front of a mountain. So what is the label you want to assign to this image? All of how dog and woman and mountain would all be correct. So it's a kind of a problem. And this was actually the time when Clip came up. It was very nice. So Clip just had a text image pairing, like having a description for this image, like the girl is sitting with the dog on the street in front of a mountain, and then you give everything in it, and you have the image. And if you have that, then it's much easier to get images and align text with that from web pages or social media and so on. So there's even a larger one now. Some of you might know this from Lion. They have 5 billion images with textual descriptions. So a clip is basically the idea of having a text encoder and an image encoder, and both they try to have a description and they try to match them to have the similarity between the text feature vector and the image feature vector. And if you learn this with many images, you have very powerful features. So if we use clip now, we can use the more images, and you can see the MAP keeps increasing here. Now, if you use the transformer network here, it gets even better. But we have a little problem here because clip is quite good for this relationship between text and images, but there are no really classes. So the problem is, if I'm searching, for example, for KFC with clip, this is what you get. And these are good results because I get a restaurant and I get some chicken nuggets and I get a logo. They're all correct. And if I take the first image now and search from this first image, that's what I get. So these are images that are correct, are somehow related to that, but there's no visual pairing. This means the clip is not very good of finding visually similar things because it just doesn't know about it. It might have tons of images showing a dog on a meadow, and they might look all different, but they offer all the same sentence. And this is the kind of problem that clip cannot deal with. Another problem is that you need very large batches, because if you have small batches, the chance of having two images that look similar, but they should be separated if they're not the same thing, is very small. Usually they use very, very large batches, so it's very difficult training these systems. And another problem is, as we have all these little tiny pairs of one sentence to one image, there's no global overview of this embedding structure because we don't have any classes. So what can we do to improve general purpose image retrieval even further? Our idea is to do it this way. Let's take a network which has been pre-trained with clip because they're very powerful, but then fine-tune this network by maintaining a global embedding view. And this can only be done if we have classes. So this means we need another set, and actually we did that building it from very many different domains. Actually, that's what we did. This was manually selected. We took images from Google Landmarks, from ImageNet and Faces and so on. You're seeing the list here. And this brought us to quite a lot of classes and quite a big number of images. So that means we have 169,000 classes, which is quite a lot, and 20 million images. And if you compare this to the set that is Google actually using internally, they got far more images, but less classes than we have. But this set is not available publicly. But if you now use this pre-training and fine-tuning at the same time, that's what we're getting now. And you can see actually that these numbers keep increasing quite a bit here. And we can now even take, so the gray things are the systems I've shown before. These are actually the two systems from before, now with fine-tuning that we're using afterwards. And if I use a larger network, it gets even better. You can see we get quite good results here with this combination of pre-training and fine-tuning afterwards. And this is quite robust. If we add some 100,000 Flickr images to the system, the MAP values still stay almost the same. So that's pretty stable. And I'm just showing you some of these results for these two last lines here. The plus and minus indicates if we have done this fine-tuning, yes or no. And this is, for example, from ImageNet adversarial, the category broom we get here, and you can see it's perfect with this fine-tuning that we used. And this is a normal system, and you can see we get a lot of misclassifications here and the crutch here, the same below. And this is just e-commerce images, and you can see again the upper rows are far better than the rows below, because of this fine-tuning that we used. Okay, this was the idea how to get good feature vectors. The next thing is we have to make this fast. This comes from the fact that usually if we have a query, this might be inside the data set or an external image from which we calculated the vector. We actually need to check all the other feature vectors to find the nearest neighbor. And this is time-consuming. It just scales linearly with the number of images and number of dimensions of the vectors. And therefore, if you get 10 million instead of 1 million images, it takes 10 times as long and can get pretty slow. There have been quite a lot of approaches for approximate nearest neighborhood searches, like tree-based approaches, hash-based. So if you have a tree base, you just follow the tree and evaluate on a subset. So you do the same thing with hash-based. You actually partition the space and you only look at a part of the space. And there are other approaches like quantization, like product quantization or graph-based system. If you actually compare these things, you can see that there's quite a big difference between the different approaches, and all the winners are the graph-based systems. So the only problem is they're all only applicable to static collections, which means you cannot remove anything, or you could remove it and then you would just find something that doesn't exist anymore. That's not a big problem, but you cannot add new images, which is bad. Imagine you have an agency and tell them not to put new images. It's just impossible. So actually, that's a problem there. But first, I want to show you how a fast image sorting graph actually works. This is the SIG constellation we've seen before. And what we do is actually we take this and take the feature vectors as vertices in a graph. And it looks like this. And how we build the graph, this depends on the algorithm. But the basic idea now is that if we search a graph, we start somewhere in the graph, and then we try to find the path to the query that we have here. So I have a little animation here, and we're always looking what is the closest in comparison to our query. And then after several steps, we actually come there. And in this case, we might have looked for the 3 closest images and we found it. And this can get pretty quick. I don't want to go into this too much in detail. Actually, this is the work of Nico Hetzel, and I forgot to mention this. All the feature vector work was done by Constantine Chao, who's sitting there. Sorry for not mentioning him there. If you look at graphs, they have a lot of different properties, and I don't want to go into all this. The most important thing is perhaps the search complexity. How fast can it be? And the next thing is very important. Is it dynamic? Can I actually put a new vector or can I remove one? These are the things that are important for us. And these are the people working in the graph domain might know these systems. We've just looked at this for the different properties here and the complexity for building the graph and searching. And you can see that there's some that are quite good. For example, another thing is can I reach every result, which in some cases is not important, but for us it's important to be able to reach every result we want to find. There are some problems here, and you can see none of them is fully dynamic. And this brought Nico to the idea to say, okay, let's build a new graph that can mend this. And this brought us to the dynamic exploration graph, DEG. I just want to point out the 2 major ideas. The first thing is that we limited the number of edges per vertex. This makes construction pretty fast. This makes it optimizable. I'll show this in a second. And this leads to a nice mixture between short connections and long connections. And the short connections are very good for finding things that are very similar. And the long connections are very good to traverse the graph very quickly. And this is the major advantage. I get yes everywhere, and I also get very good timing complexity down here. As a quartic graph, this means every of these colors has 4 neighbors. And so the topology is fixed here. And what we're doing now, we're just doing swappings to clean up this graph, and then it looks like that. You can see this, we have algorithms for that are pretty fast. And now everything is nicely arranged, and in this case, we can navigate through this graph and having similar things related to each other. If we make the performance comparison, you can see that these are the other graph systems I've shown before. Actually, this one is just a line of the industry standard, and this is a new system here for DEG, which is about 30% faster than the best other systems. Okay, this is how to make search fast. And now we come to the last part, and this is how can we visualize image collections. I already mentioned that before, that if you have too many images, you don't see anything. So these are 1024 images that have something to do with flowers. And if you're looking for a sunflower image with blue sky, you need to scan the lines to look where they are. And if I arrange them visually, it looks like this. And then you can very easily see the regions where you need to look at up here, for example, or perhaps there. And then you can zoom in there and you can find these images of interest very quickly. Here's another example. These are, again, about 1,000 high heel shoes. And if you want to buy them on the shop, this would be very confusing. And if you arrange them by their content and their look, it's much easier to look at. And I'm not saying you should be showing 1,000 shoes on one web page, but this shows the potential of this approach. So this means that if we have images that are sorted by similarity, and the similarity comes from the feature vectors and also comes from low-level feature vectors, because for our perception, also color and organization is quite important. This is very useful for stock photo agency and e-commerce applications. What you need to do is we have to arrange these images on a regular grid, because we don't want them to be overlapping. And this has to be done in such a way that things that have been very close in the high-dimensional feature domain should be close again on the 2D raster. And the problem is there are a bunch of algorithms and also metrics to evaluate this, but actually up to now there hasn't been any consistent evaluation. How good are the algorithms and the metrics, and how close are they related to human perception? And we said, okay, there are many different sorting algorithms. I don't want to list them. You might know some of them. You could also use, for example, TSNE and just remap this to a grid. This is also possible. But you could use self-organizing maps and other things. And then there are different evaluation matrices. So we propose two things. One is the new sorting system, linear assignment sorting. And also we proposed a new metric, which is called distance preservation equality. How can we evaluate these algorithms and the metrics? This can only be done by user tests, because the humans are looking at that and they should say what is good and what is not good. Users should decide about that. If we use all the algorithms and all the metrics, we need two types of tests. We need preference tests, showing two different arrangements, ask them which one is better. And we use search tests, showing arranged images and ask people to find particular images in this sorted set. And if it's better sorted, then people should find it faster. This was the basic idea. So, and these are the four sets we used. Like we had pure colors, and you can see this is a densely filled 3D space, but it's nicely laid out in 2D. These are traffic signs, kitchenware items from IKEA, and these are just any images from the internet. We used tons of different arrangement and sortings, and these are actually the arrangements that people liked most. There are definitely much worse ways to arrange them. And we did two tests. The first was preference test. So we just asked people, which of these two arrangements do you prefer? Left one or the right one? So this is a pretty easy case. So people usually would have taken the left one here, but there are other cases that are closer. And we did this with many people. And after that, we actually know what people liked. And this is a search test. Here the images were shown one after the other. And first they had to find this image here, and then you might look, oh, okay, here it is. And then you look at this, it should be somewhere here. So this takes time then, and this time is measured, and afterwards we know how long it took. And again, this was averaged over many different tests and many different users. And then we got a very clear result that our distance preservation quality was the highest correlation between user perceived quality and the metric value. So this was very useful, predicting the time for finding things on the web page if you have many different items. And for the algorithms, we found that our fast linear assignment sorting was the fastest, with still having quite good quality. So what you're seeing here is the processing time. One's for color images, and this is for kitchenware images. And you can see there's quite a big difference in dimensions here between the different algorithms, and these are actually different points from the different hyperparameters from the systems. But you can see very good sorting with pretty short time for a fast linear assignment system here. If you're interested in that, we wrote a paper which came out recently in October, where we tried to describe this evaluation and generation of the grid layouts. Okay, so now we know all we need. We have nice feature vectors, we have fast search systems, and we have good arrangement of images. We just thought, why not putting all this together? And this is actually the image exploration. The interesting thing is there's not so much research about this. In the very beginning, there were things like projections of tiny sets and image pyramids and things like that. But usually these things were only used to show more result images, like perhaps 100 instead of 10 or something like that. There are not many approaches trying to visualize a big set of thousands or millions of images. These are some older exploration systems. This was an image pyramid proposed by chance. If you click on one image tree, you have 4 images below, and it goes on like that. But the problem here is, if you want to find the Golden Gate Bridge, you wouldn't know where you need to click on, perhaps somewhere here, but it's just a guess. This is a Google Swirl, so we are here at the Golden Gate Bridge, but assume we want to navigate from here to Bergen. We wouldn't know where we need to go to get there, because all these images look the same. And this is here TSNE used on some images. And this looks nice, but it's still pretty confusing. So you can see we have a lot of faces here and outside images over here, but we've got a lot of empty spaces. We get overlapping regions. And also this is pretty hard to navigate. So it's not very easy to find the area you're looking for. And now I'm coming back to this image I've shown before. We have developed a system a few years ago, which we called pixbuffet.com, where we took a bunch of images, arranged them visually, and it could navigate, and it was just like Google Maps. And people liked this, and you can still try it. It's still out there. And so this is the basic idea. We have an image pyramid, and you can visually navigate it. And because it's visually arranged, it's easy to know where you need to go. And it's suited for a very large set. For example, pixbuffet uses 1 million images. And it's a good visualization. It's easy to understand. But the problem is, it again was static, because this means if you have one new image, you have to rearrange everything again. And this is just not possible. And also the other thing is, if you have a static map like this, it's not perfect for preserving all the relationships. And so this brought us to the idea, which brings me to the end of my talk. How can we take this idea and make it more flexible? And we do this by using graphs instead of these maps. We actually use 3 different feature vectors for that. One is we need to have good text retrieval. There we just need to use the normal clip vector. This can be changed to better things in the future. Then we use the feature vector I've just shown before, and we do the search also the way we do it, I've shown it before. And we also need a low-level feature, which is basically just a color layout and color histogram vector. But the hardest thing is, how can we make a good graph visualization? So this is a part of a graph. So if I'm somewhere, I get the neighborhood some hops away, and these are all images, I could just take them and arrange them visually. So that's pretty easy, like taking our fast linear assignment sorting. And this map then can be modified with the user. And I'll show you how this works. The basic idea is, if I'm seeing this here, I could just drag this like a normal map with my mouse. And what's happening then is that I'm actually moving out some of these images out of the canvas. And I got an empty space here. And what we're doing now is we are looking at these images which are opposite to the drag direction, which is this area here. And these are the images shown here in the graph. We've lost these images that we've moved out of the map. The red ones are still visible. The blue ones are the border images here. And we just look in the graph what is connected to this border. And then we retrieve these images. And then we get the new subgraph. And then we sort this while maintaining the previous set that we had before. This is the basic idea. And the nice thing is now I can do 2 things. If I'm doing this hierarchically, so I could zoom in, I come from animals to chicken. And then if I'm dragging it, I might come from chicken to chicken heads. And this is a very nice way of navigating. First, I have to find some animals and zoom in until I found some chicken. And again, you can see how I can move there. And I can even store my dragging approaches, because I'm just adding new things. And this makes it very easy. If somebody said, oh, no, that's not good, I actually went to the wrong direction, I could just go back and then start over from there. And if I just cache what I've seen before, I could enable this very easily. Okay, and this is the system, how it looks now. And so we got 2 different sets. I will go to the fashion set first. And actually we have different ways of displaying that. We can have a more or less images. We can change the number. So here we are in an area of watches. Just take this away. And I could make a search here. I could just look for a skirt, for example. And then this would bring me here, and I could say, I like this type of, and actually I can now start navigating to different areas here. And if I say, okay, I like this thing here, I would find similar things. So I could just jump around here and jump to random places. And if I say, okay, I'd like to have a guy with a striped shirt, then I will find all the others that are striped as well. And if I say, oh no, I want something like this, again, I can take this as my new center and navigate around here. And you can try it yourself. It's online. So, and that's it. There are two sets. There's another one here with the same set, like the Pix Buffet set. And again, here you could jump to any areas, or so if you want to find the sunflower, for example, like before, I could just type this in. And then, okay, I say I want to go to this area with who, and then you could just move around here and until you found something you like. And then if you like it, then you might get it, or you might say, okay, no, I want something with a little bit more green, and okay, and so you get the idea. Okay, so basically this completes my talk, and this is our webpage. You can find this and many other demos on there, and also we got 2 apps. You might download them if you're an Apple user. So thank you very much for your time and for listening.
Interesting talk. Do we have any questions?